So maybe we can talk about this concept, which is minimal and characteristic. As I said in the beginning, the Aryan was there. There is this concept of minimal and characteristic. For there is this philosophy here is to understand matrices and hence linear transformations using polynomials, right? And so that's what we are heading towards. And so we are associating some polynomials now to linear transformation, minimal and characteristic polynomial of, yeah. Obviously, they can be defined for many other, but we will only talk about. Yeah, sorry, I think I call it. Doesn't feel correct, right? Because then, okay, not like that, but there. Hello, yeah, yeah. Are you joining? Okay. Right. Yeah. So let's keep this one, this part of the discussion more elementary. Okay. And here we just talk about this very down to earth things, minimal and characteristic polynomial. So yeah, so let me talk about it from a slightly, yeah. Yeah, maybe that is better, right? P conductor, yeah. So we have the vector space V. Okay. Yeah, some things I've not said properly. That's why I'm saying. So yeah, so fix this thing, or just fix Fn. Okay. Fix Fn. F is a field. Fix Fn, and then you take a subspace V. Okay. Subspace, yeah, subspace V, and fix a matrix. So matrix, and then we want to look at what I will call conductor of I know what I have to say, but conductor of A in V. Okay. Yeah, but let me just check the terminology from the book better. Because there's a problem that if there is something else reserved for this term, then that's not a good. Then it's kind of immoral for me to use this terminology. Okay. Because I understand what I want to talk about, but and also you want to use some terminology, but I should not misplace them. Via annihilating polynomials, but I want it to be slightly more general. Otherwise, it takes forever. If you read the book, it takes forever to get to the matter. It doesn't have a search. Ah, right. The conductor of this set which consists of. Oh, so my terminology is wrong. Yeah, I'll correct it and I'll use it in. I correct it and I'll use that concept to define whatever. That's important. So you fix this. Maybe I'll call this W so that you are subspace. Yeah. So I'll just say that, I mean, as much as possible, read up, Artin's chapters, read up, or often and read up. Things are going to go a bit more serious. So W is a subspace, and this is big. So now I'll talk about something called A conductor. This A is not what's it called? Preposition. I'm sorry. Not that. It's called A conductor. This is one sort of word. A conductor of V in Fn. Yeah, that's a very wise term. Sorry. Yeah. A conductor of V onto W. Okay. So what is it? What is the philosophy here? Okay. The philosophy is to look at those polynomials, okay, which push V into W. Okay, which push V into W. So you have a space, you have the space, you fix a particular V, and now for this V, you define this concept. You fix this V, and let's say your W is this, one dimensional, only up 2 dimensions. So W and this is V. So you want to look at this V and this W, and then you want to ask, what are those polynomials which push V to W? I will say, what if we have polynomials? Polynomials are not. So I'm saying that polynomials in A, right? So does A push V to W? Maybe, maybe not. Does A square push? Is A square of V inside W? Okay. So that's the idea you want to make forward. A conductor of V into W is, so this is equal to all those polynomials. Okay. You want to look at all those polynomials, okay, such that gx is in this, and g of A is understood, okay, such that g of A at V goes in, where it goes exactly we are not concerned with, but our exactly is only up to whether it goes in W or not. Is in W. Okay. This can be in the language of modules over rings. This will be much better. Uh, Not really. Yeah. Yeah, but in the language of quotient spaces, it will be better, but we don't have that concept yet. If you know it, then you can view it in that way. Quotient F then by W. But anyway, this is this. Is this understood? This concept. Right? So if this is understood, then you check that W is an ideal in wrong X. Polynomial is an ideal in Fx. Look at the definition of ideal and prove this. Ideal just means that if Gx is there, Fx is there, then sum is there. Okay. If Gx is there and H is anything, if Gx is in this and H is anything, then H times G, Hx times Gx is also in this. It's like a zero. It sucks in everything, right? And when you add 2 zeros, it's like zero. These are like zeros. Check that W is an ideal. Check this. And therefore, this collection W, right? So after you've checked this will imply that, and we'll now connect this with test minimal and characteristic polynomials. But first, let me ask you this. Yeah. Right. Yeah, this is quite interesting. Okay. So let's just check that it's the ideal with ourselves. So then, because I need more of this, I need So if gx and okay, so we'll also need a notation for this, otherwise it becomes burden. So alpha a w, the notation. Alpha is just one dummy thing, and the rest is wrong, bad notation. I will need v also. And all these things we will need, right? All this information is there. So with this thing, we have to say. So now, one thing that should be clear, that if g and f is a polynomials, if this is in this, then do you see? Yeah, so actually, it's, yeah, what I'm saying is not correct. This is not correct. Yeah. You will see. It's not an idea. Sorry. But no problem. So, yeah, but you have these two. If this is in this, can you check that g, this is there? This is also in this. Yeah, don't give up. Can you check? So what do we have to check? You have to just check that. You have to just check that you take g of a plus f of a, right? And then you act it on v, right? Then you want to show this is in W. But then you know by linearity of polynomial, this matrices, matrix multiplication, you know that linearity of matrix multiplication. This is not linearity of matrix multiplication. This is just linearity of function application, right? Sum of two functions. Yeah. So I was wrong there. This thing, and then you know, right? This is in W and this is in W because of this definition, and therefore this is in W because W is a subspace. W is a subspace. Not just a subset, of course. We won't be talking much about it, but yeah, anyway. Okay. So now you tell me this is fine, right? So what is the other thing about ideals? What is the other thing that we should try to check? And this will fail, but see it. What is the other thing we should try? Yeah, that if G is just an arbitrary thing, and so one is arbitrary and one is inside. Okay, and F is in this. I mean, I can just call it alpha at this point because it's only one A and B going around, but still this. So we should try to check that this thing, the product, is also in W, is also in this, right? So what do we have to do? You have to just check that this thing, you have to just check that what does this, is this polynomial, if this is in this, if you just check that this evaluated at A, and when this matrix acts on V, then is it in W? So it's not in W. Okay. Why is it in W? Hello? No? Yes.
Yes, sir. Yes, it
Yeah.
is in W.
But why?
Sir, again, from how like the functions are defined, right? So like product of functions and so on.
Yes, that's right. But G is not in alpha. That is a problem. So this thing
Oh,
may not be in W. Correct? That is the point. Right? That's the thing, right? G of A at V may not be in W. We know that f of A at V is in W. Everybody? But G of A is not in W. Okay, I mean, is it correct? Or Hello? Yeah, is it fine, everyone?
Yes, yes,
Yeah,
sir.
right. But it is not in W, right? That's what's happening. Okay. Please tell me. I mean, if there is something which is not clear, tell me. So this is wrong. It's wrong. Uh, all right. But then I will further add this condition. Hey, should I move forward with this concept? Is it okay, or what's happening?
No, no, sir. It's
It's
okay.
fine.
It's fine.
All right. Good.
Yes, sir.
Yeah. So now we want it to be an ideal. We want it to be an ideal. That's the thing, right? So I'll add one more condition. I will say that A of V is in W. Uh, sorry. If I add this condition, see what happens if I add this condition. If I add this condition, uh, then no, no, sorry, this is not a good thing to add. Yeah. So I will just take back this bit. Adding that will do something, but that will not be interesting. So we'll just have checked this good property about W. The W is closed under addition. But now let's do the actual matter. Okay. Now you look at this thing. Take the intersection, okay, of this alpha A B W, where V goes over the vector space. Okay. So what is this? Very simple. It is those polynomials which, when evaluated at A and then acted upon V, push it in W for every V in the vector space. Okay. So this is simply actually simpler. What is Gx? Gx is just those things such that G of A pushes the entire vector space, right? Because that's what it is. You're taking intersection over everything. This was V, now it's the entire vector space gets pushed into W. G of A is a matrix, not linear transformation. We are only looking at those polynomials, and this is a polynomial, this is in the polynomial ring. Okay. Is this definition fine? Yeah. You're looking at those polynomials, right? Such that when A evaluated at those polynomials pushes the entire vector space into W. The image is in W, right? Yeah. Now you apply this, so maybe I will call this alpha AW because the V is not there anymore. Now you look at this. Now we are coming to the concept of characteristic polynomial. It's fine, but it's coming to the concept. Okay. First, let us check that this is an ideal. Okay, this is an ideal. So again, the addition part is trivial. Okay, but let us check the multiplication part, right? So if F is in the field, okay, and G is in this, something which pushes the vector space into this subspace W, something which pushes the entire vector space into subspace W, right? Then what is Fx times? Is this an ideal? Let us check. So what happens when you, so basically this thing, for any V, this should be in W. We need to show, right? For all V. For any V, this should be in W. This meaning that, I mean, when evaluated, right? right? But this is true. And then there's a fantastic thing going on. Matrices are not commuting, but FA and GA are commuting. FA and GA commute, right? Any problems? Because it's all about A.
Yes, sir, they commute.
They
They
commute,
commute.
right? That's the thing. A and B don't commute. FA and GB will not commute, but FA and GA will commute. And that is like a very nice thing that happens, right? And so we commute them, and then FA is again something, some V prime, and GA pushes this in W by definition. And so, yeah, please let me know if there is a doubt.
No, sir, no doubt.
Right? So this is an ideal. You see, when you take intersections, things can become good. That's the general principle, and you should. So sometimes you think, should I do this? Should I do that? Should I do this one? No, that's okay. But in mathematics, there are a few things that usually work. I mean, that to get hang of this, it depends from the different places you are working. But understand that I just got a hand that just break it. I didn't think much. It should work. So anyways, so this is an ideal. This is an ideal, right? So well, this is an ideal. Then So okay. So we'll just do it on this page itself. This was just a check. Check. It's an ideal, right? So an ideal in a polynomial ring. So alpha a comma w is an ideal. Wonderful. Which means that alpha a comma w, how will an ideal look like? Well, it will just be, it will just be some some g which depends on e and w, okay, and all its multiples. Is it stacked okay? Or so I'm saying that implies there exists a g a w such that this happens. There exists a polynomial which does this. Okay? So you prove this, just simply prove this. Okay, general fact about ideals. If you have an ideal in a polynomial ring over a field, it doesn't work over rings. But polynomial ring which is over a field, it works. But if the polynomial ring is over a ring, it may not work. So if you have an ideal in this, okay, then you just take the polynomial in I which is of least degree and show that everything else is a multiple of that. That is what I've written. There is a GAW, this nice GAW, which basically has all the information of the ideal, right? Its multiples with fx give you everything you need. Everything that is there in the ideal. Okay. So this ideal will be just some gx and generated by that. And here generated means in the sense that multiplication from fx. Okay. This is a fantastic thing. It also happens in integers. You can prove it. These are some general facts about ideals over principal ideal domain. But yeah. This is just Euclidean algorithm. I've told you, take the polynomial with the minimum degree which is there in I and show that everything else is a multiple. If it's not a multiple, there is a remainder. It's smaller degree, some contradiction. The way you prove the basic thing is but you should do. So there are a lot of work to be done. So this is the situation. Right. And now we look at, basically this thing is generated. And here you understand the sense in which I'm using the word generated. Is generated. So this thing is generated by this. Fine. Now I will move forward. Now we put w equal to 0. And what happens? That is the characteristic polynomial comes with that, right? So when you take w equal to 0, then you get alpha a 0. And do you see that Cayley-Hamilton theorem is just saying that the characteristic polynomial is in this. Correct? Because the characteristic polynomial, if you call it px, then you know that p of a is 0. So you know that p of a for any vector is 0. And so p of a is precisely in this when w. Is it correct? So when you put W equal to 0, then we are just looking at those polynomials which fill the vector space, completely fill the vector space, completely take the vector space to 0, right? And those collection of polynomials form an ideal, and the characteristic polynomial is there in the ideal, right? The characteristic polynomial kills, that's Cayley-Hamilton theorem. But more interesting, more interesting than this is, so this is there, but more interesting than this is we would want to look at the generator. The generator, and this I will say more concretely as well, because but this is the generator of alpha is 0, which means all just put 0 here now, put 0 here, or just put g of a equal to 0, all are same, 0 matrix. Generator of this is called the minimal polynomial. Minimal polynomial of A. And as I said, this is basically the polynomial of least degree that is present in G. There will be a unique such thing, and if that is the characteristic, that is the minimal polynomial. Correct? So with this, we get a art and basic easy definition, which you will find in the, easier text, so to say, is the definition of minimal polynomial, right? So, yeah. So so I've defined it, but if I want to say it, I can say it as the dimension of some space, but right, so it is a generator, right? So it is a generator. So if you look at Gx, such that G of A is equal to 0, this set, right? This set is generated by some polynomial mx, and this mx is called the minimal polynomial. That is one definition, okay? And then you can see from here it follows the minimal polynomial divides the characteristic polynomial. From now on, I'll write characteristic polynomial like this. You know that this is equal to this. This is Cayley-Hamilton theorem, because we know that characteristic polynomial is in that set, and everything in that set is a multiple. So minimal polynomial divides the characteristic polynomial. But we want another definition of minimal polynomial. So minimal polynomial is a polynomial of least degree which annihilates this, right? So what does that mean? So let's say that the minimal, start writing some concrete things. Let's say that the minimal polynomial is this, I don't know, let the degree is d. Then what do you have? You have that g of a is equal to 0. Coming back to the old thing, right, which was used in that IIT JAM question. This is equal to 0. That's what it is, right? I mean, so this is minimal polynomial. This is m. This is the polynomial such that everything else is a multiple of this. Everything else that kills a is a multiple of this. This and d is the smallest, right? It's the smallest d for which this happens. It's the smallest d for which this happens. Right? What does it mean? This is true, but it is the smallest d for which there is a linear relation between I, A, this is I here, identity. Because what else will you put? You can just put a number there, it's all made. I, A square, and to the power d is the smallest d for which there is a linear relation. For smaller d's, there is no linear relation, which means they are independent, right?
So then it means that the set a squared up to ad is what is that? Dependent.
Yeah, that is true. It's dependent, and up till d minus 1, it's independent. It's
Yes,
minimal.
yeah, that's what I wanted to say. Up to d
say.
minus 1, yes.
Right, exactly.
Yes.
So this means that if you look at this potentially infinite set, and then you take the vector space generated by this, call it our old W, then dimension of this W is the degree of the minimal polynomial. Because that's what dimension means, it's the smallest generating set. And we know the generating set comes from the first finitely many. And the D, you have to go till D to get a relation. So it means that till D minus 1, they are independent. But how many are there till D minus 1? There are D of them, because GP0 is there. And that D is the degree of the minimal polynomial. So the minimal polynomial can also be defined like this. These are the basic relations and notions where we are using different theories, different kind of things. Without this theory of principal ideal domain and so on, generator, you cannot say this nicely. Right? There is a multivariable version of this, but it's more complicated because then it's not a principal ideal domain, and probably maybe you have to use null-Stalin-Zards. I think there is something called, but I should not just throw words like that. I'm not sure. Actually, myself. So yeah, actually, sorry, I'll take that back. That is probably wrong. We'll see that. Okay. Yeah. So read this as much as possible. I've given you some work, the ideal, basic ideal theory, and so on and so on. And then we will meet next week on Tuesday. Tuesday is 8:30 p.m. I suppose, right? We'll meet on Tuesday. Okay. Right.
So Tuesday 8:30, sir, next.
Right, Tuesday 8:30. But see, now you have to really set it up. You have to really put in the work, yeah, all of you. And if needed, you can go through this video if needed. You know what to read, you know what problems to do, and you have to just do. Yeah, put in the time. You have today, you have tomorrow. Try as much as possible. Okay.
Yes. Yes.
Yes.
The ideal things goes to Messi. Can you just give us the questions in the mail
Which questions?
from the ideal?
Oh, from the ideal, you want me to give questions in the mail. Okay. 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 I'll do that. Okay. Yeah, I'll do that. And all of you are okay. So if there is any things, then you can tell me. We'll meet on this. But you see, we are really doing linear algebra on a serious. Okay, so usually you'll see Nakayama lemma is not discussed in linear algebra course. Okay, it's not. But you see, we're trying to just see that their things are not difficult. Yeah. So over the years, I've seen that things actually become they are sort of related. So, and it's going to be very easy for these things. We'll see. Next time we will try to do the problems from IT Jam and that, and let's see what we'll do. Or maybe we can do multivariable calculus on Tuesday. Maybe we'll do multivariable calculus from Apostle Volume 2. All right, yes. Bye. Have a nice day.
Yes, sir. Thank you.